smoothly. Dear Professor, now over to you. Welcome in this session. Now you can start your lecture. Thank you.
Thank you, sir. Thank you, Dr. Mehra. Um I also regret for the technical issues from my side for last 2 days. I think we can go directly to the session. So
Yes, sir.
start sharing. Am I audible to everyone?
Yes, sir, you are audible.
Yes, sir. Okay, I start sharing with my screen. Yes. Is my PPT is visible to everyone?
Yes, sir.
Okay.
Yes, sir.
Yeah, fine. Thank you. Then, okay. So I'm Dr. Pradeep Natarajan, and I'm doing my postdoctoral research associateship in Center for Bioinformatics and Computational Biology in NIT National Institute of Technology, Rourkela. And today we're supposed to discuss the topic is homology modeling or molecular modeling. Okay. Okay. Why we are going for this? What is the need for this? Okay. Okay. Fine. What is the need for the proteins structure? What is the significance of the protein structure? Why we need the protein structure? We need protein structure because the protein structures will define you the shape, complementarity, geometry of the protein, and it will define the conserved residues position and functional sites, ligand cavity sites, and clefts where the protein, another protein can go and bind, or ligand drug molecule can go and bind, and how the relationships between one protein to one protein during the evolution, and those evolution relationships can be derived from the protein structure. And one of the most important methodology in drug designing is molecular docking. For molecular docking, we need a receptor structure, right? Because receptors that represent the proteins will be defined based on that molecular docking will be executed, right? And then in QSAR studies, we have 2D QSAR studies and 3D QSAR studies, quantitative structure active relationship studies. In this, structure plays a major role. So for that, all these cases, we need the protein structure that represents that particular protein, or the interested protein we are involved in study in our studies. So protein structure is significant, and so we are supposed to go for define the structure. In structural genomics project, we have many protein structures have been experimentally derived, and the three-dimensional structures were resolved and stored in databases, right? In that cases, just if you're comparing between the known and the unknown, you can see in the blue circles where will be the unknown proteins. Unknown protein means structures that are not defined for these proteins, and the circles with the red color defines the proteins with the known structures. That means we are more, there are lot of proteins are there to define the structures. In such way, we are involved in defining the more structures, right? That can be experimentally validated, or it might be the theoretically validated structures, right? In that case, if comparing with the just number, this is the structure showing like example for the number of known structures with known protein, and number of the structures with unknown structures, proteins with unknown structures. So in case of, see, okay, let's generally discuss what is the why we need to go for the traditional structures, mean native structure of the protein, because you all know like Proteins will be the amino acids are the basic units of the protein structure. So these amino acids are like beads joined in the form into the thread like a garland. But these amino acids will not exhibit its function when it is like an amino acids or polypeptide chain. But when these polypeptide chain try to fold into a two-dimensional structure and tertiary it folded into a three-dimensional structure, it will fold into the native structure. I mean, energetically minimum energetical structure. In that case, it will be termed as a protein folding state, I mean native state or energy minimized state. In this folding will take in step by step. Like you can see in this image, like native state and molten globule state. Like the intermittent state. Molten globule state is an intermittent state from the amino acid sequence to native state. It will fold and unfold. During this folding, steps will be like this image. So this protein folding will take off lot of entropy will be released, like energy will be released, energy will be absorbed, and such that the amino acid polypeptides will fold to form a native structure, right? In that case, this folding will not take a single step. It is a multi-step process. Sequence polypeptide chain to getting a native protein structure is a multi-step process, and this process will be executed like here, like this image. You can see like here from this upper end into attain some energy state, low energy state with some fold, and from that fold again it will turn to bind, fold again to get low and another low energy state, and then again it turn into for another low energy state. Here, so you can see this from here to here, and then here to here. This from one low energy state to another low energy state to get the at the bottom to get the lowest energy state. So this will be defined as the native state. Here you can see the molten globule state. This is the molten globule state. You can see the secondary structures inside the chains or inside the barrels looking like representing the beta sheets. Here, the secondary structures are not fully properly arranged or properly folded. That can be we can see in this molten globule state because it's transition from high energy state to low energy state. You can see the value like graph high energy to low energy state. Okay, I mean higher the negative, the lowest energy, right? So from higher energy to lower energy negative score, it will get into folding to get the native structure. So this fully folded native structure only, I mean, it can exhibit the functional activity. So the structure is important, and this defining the structure makes very important process in defining. Okay, in defining the process, mm, so why we are going for homology modeling? Because we have a traditional methods, scientific methods like X-ray diffraction method and NMR method. Okay, shall I move this? Okay, fine. Okay, here X-ray diffraction method. In X-ray diffraction method, see, we'll be mounting some pinpoint, we'll mount some crystal, and monochromatic X-rays will be passed onto this, and we have X-ray plate here. We will have the diffractions, and from this plate, it will be red. This will be the X-ray plate. After that, we will find the diffractions like these spots. Okay, some spots, and these diffraction spots will be compared to the mathematical model, and based on both, we'll be defining the X-ray crystallography structure, like XRD structure. Okay, but In these, drawbacks are only the proteins that can be modified in the form of crystals can be studied, so that we can mount on the pinpoint. Okay, so excuse me. So the proteins that are cannot be crystallized cannot be studied, right? Only the proteins that can be crystallized and can be mounted on this pinpoint, and then we can pass the x-rays and we can study the traditional method as X-ray diffraction method, right? And one more thing, these crystals are not the native state or native environment of the protein. See, this is my environment where I live. But for in case of proteins, crystallized structure will add the materials such that it can be packed into form of crystals, right? So that is not the its native environment. So native environment mean it's not native environment, so it will not be a native structure. We may find native structure, but it will be not act as similar to the native environment. So we cannot imitate the native environment in crystallization process. So that is one method, one of the drawback method in this method. And one more thing is it's a very time consuming process and expensive process. And second thing is another method is NMR distance measurement method. So NMR resonance structure method, here we'll have the magnetic resonance magnets, two magnets. So these magnets will be meshed. So here, so here we'll be giving the electrical charge to these magnets, and the proteins that are soluble are kept in these solutions here. So when uh, current is passed through these magnets, electrical or magnetic waves will be formed here from this magnet to this magnet, from direction or unidirectional or bidirectional. It can be done both. In that case, we'll be plating one plate here. So based on these resonance structures and the diffractions of the magnetic field, we can find the structure of the protein here. And drawback is in this method, only the protein that can be solubilized or that can be solubilized with some adjuvants can be studied with the structures. So that means very less number of proteins, isolated or pure form of proteins can be studied in this method. And one more thing, it can be studied more as a complexes rather than a individual proteins. And it is also a very time consuming process and costly method. So with these traditional methods of defining the structure like X-ray diffraction and NMR studies cannot be done in every small laboratories. So here you can see this just alternative method than the X-ray and NMR is homology modeling, because reasonable models of protein structure can be developed. Are everyone following? Hello? I think
Dear participant,
Yeah, we are
if you
hearing
have
you.
any
Yeah,
question,
You're following.
you are permitted to unmute.
yeah, like I thought like it was muted by everyone, so it was very plain. I'm talking to myself like so I had any doubt. Yeah, fine. It's good to hear everyone is following. Fine. So we have traditional methods like X-ray crystallography method and NMR method. So these are more laborious process, costly process, time consuming process, and it needs high-end sophisticated instruments for that. So every lab cannot be offered. That is the first reason. And time consuming process, cost effect, more costly method. So what are the alternative methods for this? Like predicting the protein structures. In that case, when it comes for alternative methods, homology modeling or comparative modeling of the proteins will be the best way for predicting the structure. We have already methods like homology modeling, threading, and ab initio method. In these three methods, we can define homology modeling and threading both as knowledge based method. That means both in homology modeling and in threading process methods, we need some pre knowledge or prerequisites like similar structures for the proteins we are interested to study. So these two term, homology modeling method and threading method, we term as knowledge based method. And ab initio method is term we can term as like de novo. It is like developing structure from the scratch. So homology modeling and threading like knowledge based method and de novo method. Okay. In that case, what is the homology modeling method? So in this, we'll go uh, more deep in this next slides. So I'm just skipping this portion. So for like, I'll be explaining this. All the thing we'll be doing in a Python script and Modeler. A hands-on section also will be doing, like Dr. Mahesh has said, we'll have hands-on session also, if possible today or next session. We'll have a hands-on session for this. Okay, I'll make you like everyone as possible to make the, you can build your own protein structure for the your interest. And threading method, in threading method also we'll be explaining more in next slides. I'm just giving introduction. Ab initio method, de novo method. Okay, we'll see the first homology modeling method. Homology modeling or comparative protein modeling method. Okay, the name itself we can see it's a comparative protein modeling. That means we need some uh, similar structure that are already defined. Okay, so it is a most reliable method when compared to the other methods. Okay, because it is an exploration of the new protein structure from the existing validated structures from the databases. Okay, that will be termed as a target and template. I'll explain what is the target and what is the template. Okay, so this is the basic workflow. Here you can see the interest of protein sequence, nothing but amino acid polypeptide sequence. Okay, in this we'll get work for the sequence alignment. Okay, sequence alignment from the databases. We'll go for search. Okay, and then we are getting the good structure. Here you are searching sequence against structures, not sequence against sequence. We are searching sequence against structures. Okay, PDP, and then you'll get good structure, that is a template or homolog. You might be familiar with the homologs, orthologs, right? Homologs means similar structure, similar function, similar origin, right? That means homo means similar. We'll get the homolog structures that are similar to the secondary structure of the protein we are interested. Okay, I'm just using a overflow here, and then we'll get the structure. We'll improve the secondary structure, and then we'll build a model, and then we'll minimize the model, and then we'll take for the model structure for our study. So this is the normal regular workflow of the homology modeling. Okay, and what are the steps involved in this? Like I have shown here. For our easy clarity and clear-cut explanation understanding, I made this workflow. Steps involved homology modeling. So first step is identifying the template. Then what is the template? Okay, template is the three-dimensional structure that is already defined and validated. That structure, we can't take all the structures as a template. Only the structures that are similar to our sequence only should be considered as a template, and I'll explain that. And then that involves the initial alignment, and then the improvement of the alignment, and this identification of template and alignment is the major and important step in the homology modeling, because If you're identifying the wrong template with non-similar structure sequence identity, then the entire model we have generated will be the wrong, and we'll face many issues. And then second step is backbone generation, and then loop modeling and side chains. So this will be the second major step, and then refinement and nothing but building a model, right? But after all these steps, wha- equal to these all steps, the single step similar to all the above step is validation. Whatever the structure we have generated, it should be validated. Unless until we are validated, we shouldn't consider that structure for the studies. Okay. And okay, I have said the template. We should select the template and what is the template, how the template should be selected. Okay. In sequence alignment, when comparing our sequences to the traditional already predefined structures from the database, we have sequence similarity and query coverage and alignment. In this, we'll get the color representation for the identical residues avoid the sequence and the known structures. Fine. This is represented here. I can see if it is 0% to 25%, 50%, and 75%, and more 100%. In this, detection of homology is first done, and then alignment accuracy is done, and then quality of the model is checked, and then speed of modeling is checked. So these are the limitations. These are important, and these are the limiting factors in the modeling, homology modeling. That is, one is the speed of the complete modeling and quality, how good the model was generated. And next, before that, alignment, accuracy of the alignment between the target template sequences, and first of target mean template selection, that is nothing but detection of homologue. Okay. In this sequence identity, we can compare medium resolution NMR subset specificity and molecular replacement of crystallography supports cytochrome mutagens through visualization and errors. So nothing but less than 30%. If you are considering homologs with less than 30%, we will get like more errors. And 30 to 60%, it can be like side chains should be verified again with this template. Templates with having 30 to 60%, we are selecting as a template. After generating the model or building the model, we should concentrate on the side chains for the corrections or protein model refinement. If it is more than to 60 to 100, 60 to 80 or 80 to 100, then it should be compared with the resolutions of the structure. Okay. So these are the first step. We'll get the polypeptide sequence, and that polypeptide sequence is compared. How we are comparing? Based on what we are comparing, like residue to per residue pairwise alignment we are performing. Okay, we will be doing with cluster W, or we can perform with cluster W or cluster X. Cluster X is an offline tool. Cluster W or plus Omega 2 is like online tool. It's a web-based server. We can upload our sequence and we can get the alignment file. Okay. So first step, this is the basic to the template. Identifying the template. Right now, going for the first and basic step. So template identification. What is a template? Template is nothing but homolog that is having similarity or identity to the our interested sequence or target sequence. The sequence that we are having, that we are interested to generate the model, is termed as a target sequence, right? And for the target sequence, we are searching for the template structure. Fine. and how we are selecting the template structure. So for identifying the homolog structure from the databases, we need the sequence, and we'll search against the database of structures. This can be done using BLAST. BLAST, you might be familiar, nothing but BLAST basic local alignment search tool. And then we can have the SciBLAST. We have three, multiple BLAST. In that we can use like BLAST, BLAST P or SciBLAST, and full recognition methods can be used. These can be used and compared for the active site motifs and functional annotation of databases, like those biological information can be used from the template can be used. Okay, and what is the importance of the sequence alignment, why we need to perform the alignment to get the template, like is because very crucial is sequence alignment quality. How much target, like our sequence and the template sequence, are aligned per residue is more important. If more gaps are there or more insertions, deletions are there, it will be representing a non-homolog for the target. Okay, so in auto alignment also, we should be consider the alignment, and it should be considered because this alignment defines the template, and the template defines the quality of the entire model. So target sequence alignment is more important. And how we will perform that target sequence alignment? So yeah, sequence alignment programs we have. I have shown here as a series of programs developed from the based on the year it has been developed. 1970s, like dot plot method and Edelman-Wunsch algorithm, global algorithm was defined, and this algorithm will define the global alignment. Oh, 1 second, ये क्या हो रहा? One second. What is this? ये क्या हुआ स्क्रीन में? आपको ये दिखा रहा मीन्स everyone available to scratch? Hello?
You want to erase the pen?
Yeah, this one, these all these things
Back
scratch.
to where you pick, go back to where you pick the pointer.
Pointer
Alright?
is
Yeah,
yes,
where you pick the pointer, below you will see eraser.
yeah, but
You're not there, you're almost there. No, not there, not there. The pointer, yeah, yes. The eraser should be highlighted. Yes.
but it's not on my slide.
Just click on any of the ends. It will. No, you have to pick the highlighted any of them. Then
Yeah, yes, but not sure. Yeah. See, यहाँ पे है.
okay, just pick only eraser. Don't just only eraser. Then go back. Now, click. You must click on the link. On any of the links. No, you have not clicked on any of the links. On any of the links. Good. Now use it to click on, use it to wipe on.
ये तो क्या हो रहा? I mean, like this is not going. I mean, this is very peculiar one, a new one to me.
You can still see the slide.
Sir, please again click there the share option. Yes, erase to all.
Erase to all, not going, sir. It's not on the screen actually. See, it's not on the slide. Still, it is here.
Okay.
Not on the
Hmm.
slide. Slide यहाँ पे है ना? So slide के ऊपर है.
Okay. 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 Okay.
Slide के ऊपर का इस
Uh,
तरह. That's what. Shall
is
I
there
close?
any more app in your system?
But we can actually see. Maybe you can go ahead. We can see the slide.
No,
Sir,
I
you
can.
have one app which is open in your system, Screen Writer.
Ah, yes, sir. I mean, I can go with this here. Like,
Okay, I think this is Zoom. Yes, yes. Now
yeah,
it's fine.
this is fine, but uh, sharing में आ रहा है ना?
No, screens are visible. Screen is visible.
Okay, right now?
Yes.
I think
Okay.
you can see
Same
this.
same promise.
This is
Just
not on
one
the
minute, sir.
slide.
Just
This is
1
not
minute.
on the
Uh,
slide. Yeah, yeah. This is not on my slides actually.
okay, okay, okay. Just 1 minute, sir. Just 1 minute. Please unshare the screen.
Okay.
Please unshare the screen.
Yes, yes, sir.
Yes. Just 1 minute. So when you will share the screen, there is annotate.
Okay, sir.
Okay, that was selected from your side.
Oh,
Yeah. So please unclick there. Then you can do each and everything. Now you can share your screen, sir. Please share your screen.
yes, sir. 1 minute. I'll share the screen. Is this fine, sir?
Yes,
Yeah.
it's fine. It's
Yeah.
fine now.
Yeah.
Yes, fine.
Okay, good. Thank you, sir. Sorry for this interruption. I thought it will be not visible for you all, so I made this clear. Here, Needleman Wunsch algorithm is developed for the global alignment. Okay, and dot plot was developed by Gibbs and then developed in 1970s and later 1980s. Smith-Waterman algorithm was developed that is for local alignment, and in 1880s FASTA developed by Pearson-Lipman and BLAST from Altscher. 1990s, 1995 OBLAST was developed, and then from the BLAST, BLASTX, Gap BLAST, and SciBLAST was developed, and then to early 2000s it was Mega BLAST, and then late 90s we have developed FASTA and PyBLAST, and then have developed into Saha and BLAT. So these all these alignment algorithms and methods still we are using and more familiar is BLAST and FASTA. But much older, but they are good at alignment. So we'll be using the FASTA and BLAST. So I'll explain how the FASTA alignment tool and BLAST alignment tool works on the background. Okay. Sorry. Okay. Excuse me. Yeah. If you are giving the sequence, our target sequence of our interest, we are supposed to generate the model. For example, consider sequence A. And our sequence, when we are giving in the FASTA tool, we'll have one window. In that window will be, 1 second. Okay. Um, Sequence for query. We'll pasting our sequence here, and then we'll be running the FASTA. In this sequence, whatever we are given the amino acid sequence will be uh, theoretically broken into tuples. K tuples. You can note this. K tuples. L E S. Okay. K tuples and these like small words. Okay, identical words, and those words from our target sequence will be compared to the sequences in the database. B represents the second sequence. Like that, similarly, it will search for the third, fourth, and all the database sequences simultaneously. Okay. In these tuples, you can see here the dark. This is the one tuple, another tuple, another tuple, another k tuple, another tuple. So similar tuples from the our target sequence and the template sequence will be matched. You can see here with the scoring matrix. With the help of scoring matrix, it will give the score for match and the mismatch and the gaps present between the two sequences also. Okay, in that case, it will join those similar sequences to give the sequence. Final output sequence you can see here. Okay, this is how FASTA works. Then BLAST, basic local alignment search tool. In this, as in FASTA, BLAST sequence will be divided into words virtually, not literally. These are the amino acid sequence. For example, in this amino sequence will be broken as the words, okay, as shown here. And these words will be searched with the template sequence or deposited sequences in the database. Okay, we'll be searching against in our homology case, homology modeling case, we'll be searching against PDB. Okay, where three-dimensional structures are deposited. Okay, these three-dimensional structural sequences were deposited, and those the sequences were divided into words, and these words are compared to these words. So break database sequences into words and then it compares. Okay, in BLAST we'll have more number of shortcuts. Okay, to define the databases, like PDB is one of the database, structured database. Like that, we'll have NR database. NR nothing but non-redundant databases. And ref sequence gives the RNA sequence entries. Refseq genomics will give the references from the genomic sequence project, and ESTS gives the express sequence tags from the all these organisms, and proteins by automatic translation it will generate the compare the protein sequences on UniProt. And in PDB it will compare with the three-dimensional structures from the protein data bank. Okay, so once we and going in hands-on, you can check this. It will be, I'll explain again. Fine. So in FASTA, it will compare with the known tuples to the template tuple, homolog tuples in the database. And in case of BLAST, it will compare the words to the known words in the database. Fine. So when compared to BLAST and FASTA, BLAST is more speeder and user friendly, and then more statistical analysis is available in the BLAST when compared to FASTA. So and BLAST is more accurate than the FASTA. So we'll go with the BLAST only for generating the template structures. Fine. And then, so BLAST, we have developed many types of BLAST. In this, we can see the program BLAST N, BLAST P. You can see BLAST N defines the nucleotide. BLAST P defines the protein. BLAST X defines the comparison between the query and the out database sequence. T-BLAST N shows the translated BLAST N. and T blast X shows the translated blast X. Okay, what's the difference between all these types? Or nothing but the query sequence and what sequence it is compared and how they are aligned and the alignment level of the query and the database sequence. See, in blast AN, we will giving query sequence nucleotide. Nothing but what the sequence we are giving to the blastian to perform the search, similarity search is nucleotide sequence, and it is compared to the nucleotide sequence in the databases. And alignment is done between nucleotide sequence to nucleotide sequence. So that is blast N. In case of blast P, protein sequence is given as input and it compared to the protein sequence database. And alignment is also done with the protein level. Okay, amino acid sequence to amino acid sequence were aligned. But in case of blast EX, you can see the query is nucleotide, database it was searched is protein. So here alignment is done with the protein sequence. The input sequence is translated. Nucleotide sequence is translated to protein sequence or amino acid sequence, and database sequences is considered protein sequence only considered, and these were aligned. So this translation is defined with blast X, nucleotide to protein. In case of T blastn, translated blast N is protein is compared to the nucleotide, and alignment level is done with the protein. Here database nucleotide sequence is converted translated to protein, and this protein sequence is aligned. This represents the T blast N, and T blast X input is nucleotide sequence, database sequence is also nucleotide sequence, but comparison and alignment is done with the translated nucleotide sequence, that is protein sequence, and here also with the protein sequence, and alignment is done for the protein alignment level. So these are the types of blastics. In case of homology modeling, we will be using blast P against structured database. Here we'll use sequence generally, but for homology modeling, we'll be using structured database PDB. So PDB protein structures sequence will be compared here in for homology modeling. So this is the type difference. Okay, blast programs are different types: blast N, blast P, blast X, T blast N, T blast X. What is the difference? Queries sequence query and database of the sequence query type and the alignment level. So this is the basic difference between the all types of blast programs. Okay. Okay, here we can see the color representation of the sequence search. After searching from the blast, we'll get the hits, and those hits will be represented with the graphical representation and alignment representation. Both you will get the both graphical and alignment, and this is the graphical representation. Here you can see the index here: blue less than 50, 50 less than 100 hash, and less than more than 150 and more than 200, 200 greater than 200. Okay, here this color represent like red and pink will give the more good and identical. Identical. Okay, blue or good and sorry, good and similar, right? And black, you will sometimes will get the black here. So black, or we shouldn't consider the black because they're not homologous. Okay, more than 30% only we should consider. Okay, in graphical representation, we'll have a twilight zone like 0 to 20 will get black. Okay, 20 to 30 will like twilight. Twilight zone. 30 to 60, they are good. Good plus secondary structures should be refined after modeling. Okay, and 60 to 80, they are good and refined directly. Small refinement is done. Okay, 80 to 100%, they are very good. Okay, based on these, okay, we have to consider more than 30 to 100. These uh, structures having identity or similarity score more than 30% should be considered. Below 30, we shouldn't consider it in any cases. If you are considering the structures templates with less than 30 regions following in these, will get many errors. Okay, so which the homology identity should be more than 30%. And the alignment method will have the description like this: the sequence SHA number and its description, and the identity score, similarity score, and its e value. Here e value should be higher than negative. That means higher than negative means it's lower value, right? Higher than negative is the lowest, right? So lowest e value should be considered. Alignment, this is what alignment is done. Sequence like global alignment and local element, both elements are done in like matrix. I'm just showing this scoring matrix for two sequences here, but in case of sequence A and sequence B is compared here, but in case of databases we'll have multiple sequences, so thousands of sequences, lakhs of sequences should be compared. So we'll be going with the tools like blast and faster. Okay, कुछ stuck हो रहा है sir, मैं like, is it audible? Am I audible to everyone?
Yes, sir.
Yeah, okay, I think my system has stuck or network issue. 1 second. PPT has stuck now. I think some PPT has stuck. क्या हो रहा?
सर आपका पीपीटी हैंग हो गया?
No, not it's not responding.
Okay.
What is
Uh, please close this one. It will take time. It will take time.
yeah,
Please wait.
I'm just going with this.
Yes, from this place you can cancel.
Yeah,
Close and then reopen. Okay, sir.
yeah.
Reopen.
वही कर रहा था पहले तो वो भी not showing this one also.
I think your PPT is too much heavy.
It's a like large one.
Yes, maybe because there are many images.
Yeah,
That's why.
images and animation also more. So
Yes, that's why.
actually, it's a more important topic, sir. So I have
Yes,
kept
yes.
all the detailed versions,
Yeah,
detailed
I got it.
things.
I got it.
Hmm.
I am
Yeah,
also the
fine.
participant of this event.
Yes, sir, sure, sir.
This is not my subject. I am mathematician.
Sir, actually, there is no science without mathematics, sir. I believe that.
Yeah, yes, I understand. Everything
That
is mathematics.
yes, sir. Uh, so shall we start? Resume, sir.
Yes,
Yeah,
you can
actually,
start.
consistent.
Dear participant, dear participant, if you have any question, you
This
can
one has
unmute
updated.
and you can ask your
It's really
question. Okay.
perfect.
If you are finding any difficulty to understand or any doubts, you can raise or you can interrupt me any time. Please don't hesitate to interrupt the session. You can interrupt and you can raise the doubts.
That has been overriding, overriding. My exam has been overriding.
Okay.
My paper exam has been overriding. Section grade has been overriding. No. Can they hear me?
So yes, I can hear, but I'm not clear. Hello. Any I mean like any participant is asking doubt or it's an interruption. Is it fine to resume? So as I have shown the previous slides, the alignment is more important. In this case, you can see the green sequence is the query sequence and red and another sequence is a template sequence alignment. Okay, here we have introduced two gaps. Sorry, I have introduced the gaps here, right? 1, 2, and 3. Okay, so that we can attain maximum alignment, right? Here you can get the maximum alignment so that you can get a stretch of a similar identical pattern sequence. But in case here we have introduced gaps or insertions in another point of sequence such that it can get more same kind of identical sequences that are matching. Okay, here we can see here these are identical. Yeah. Here the residues are identical. Okay. Here. Okay. Then okay. Here these residues are identical. You can see these are similar. Here they are similar. These are identical. Now you can get the difference between identical and similar. See here arginine is arginine, arginine, arginine. So they are identical. Here, isoleucine and valine. So they are similar. Similar, nothing but same physiochemical properties. Okay, amino acids with same physical chemical properties are said to be similar, such that we are introducing gaps here, right? So we can get more number of uh, identical stretch. So in that case, see here. So we are just improving the alignment from here to here. See, you can see the color difference gradient with the structure. The sequence with the green, right, and the red, and the blue is mentioned here in this color. Okay, orange. The blue sequence are getting this one. Red, we are increasing the more matching to this one, right? Here, introduction of gaps here are making the sequence structure as in this blue. The bottom one is blue. So this is represented here in blue color. Okay. See, this gap we introduced here reduce the structure to this shape, right? The only these two amino acid residues were skipped and the gap was introduced here such that this alignment can be identical. That increase the structure from here to here. Can you observe this secondary structure here? So this is alignment improvement. Okay, this is a template. The green one is the template or query sequence. The template is arranged. We are arranging to the similar to the query sequence. Okay. So this part is like improvement of the alignment. Okay. This can be done manually and even with the code. Okay. And template quality. After selecting the template based on the query identity score from the blast search, identity score, and similarity score, based on this and alignment, and then we'll check with the alignment, and then we'll check with the quality of the template. So based on this, we'll select and e value, e value. So based on these all, we'll select the template. Fine. After selecting the template, we have to select. We have to check the quality of the template. Okay. So because template is a crucial one. If you are selecting the right template, you'll get the right model. If you are selecting the wrong template, you'll get the wrong model. So if you're having the template with highest identical score and high resolution, it is not a good template. If you're having the highest identical score and low resolution, then it's a good template. I'll explain why. See, percentage of the identical residues when compared less to the aligned residues will get the safe model. If you are selecting the template following and these residues, here we'll get the good models. If you are getting this, here you'll be getting the wrong models or worst models. Okay. You can see here, this is the selection with the alignment with the template and the target. You can see colored one or the uh, with the good resolution structure template, like this one, second one, 90% identical and 1.5% resolution. This is a good one, right? And here we had get the 3.5% resolution. So not a right model, right? So why we are searching for the resolution? Here, after selecting the template based on all this, why we are searching for the resolution? Because resolution is also more important. See, resolution is nothing but ability of our eye to visualize the two individual things, how far they are. Simply say like how much they are separated to each other. Okay. If some particles are there, let us consider some particles in some space, like some rice. If you take some rice in your hand, and if you can visualize the two individual rice, that how much you can differentiate the distance between the two important rice. That is resolution. Okay. In this case, if two atoms, if you are able to differentiate the atoms, two individual atoms separately, how much you are able to separate, so you can visualize the two atoms differently is termed as resolution. You can see the image here. This is the on atom on molecule with a 4 angstrom resolution. You can see how it can be separate visualized. In case of 3 angstrom, in case of 2 angstrom, in case of 1 angstrom. So low resolution gives the high visibility. Okay. So the templates with low resolution and high identity should be considered for the as a template for model building. Okay. Then, and this is the script, modeler script will be running, but I'll explain in simpler method. I'm just showing here. And this is like simplified another method, like just to align the structures, and then after alignment we'll be generating the model, and for assessing the model we'll be giving the scoring method, like dope score method and J341 genetic algorithm scoring method. So here we are insisting generate 5 models, sorry 5 models. And this is a basic example code, but in hands-on session I'll be giving the other files I'll be sharing. Okay. And then after selecting the template, after alignment, after improving the alignment, we'll going for the model building. In model building, we can be I have just separated into again sub headings, like for easy understanding. So in this model building, we can say like framework construction or backbone construction. So this is like averaging the position of the target sequence, that is our sequence, interested sequence, and locating the atoms corresponding to the template, like in XYZ coordinate. For example, see X, Y, and Z coordinate, and see, this is for I think proline or let us say glycine. For glycine amino acid is the smallest amino acid with more steric clashes. Let us consider this glycine. So glycine, carbon atom of the glycine. Here is the carbon, and here is the nitrogen, and this is alpha carbon. Let us say. In this case, from x-axis, from y-axis, and z-axis, the position of the alpha carbon. X-axis will have one value, y-axis it have one value, z-axis it has one value, right? So on some x, y, something will be there, right? Some value will be there for the position and the coordinates. Yeah, like for the presence of alpha carbon of glycine in some three-dimensional axis. In that case, it will be comparing the template coordinates with the target uh, s- amino acid atoms. Okay, and it will be averaging the positions between those, and it will be comparing, and those positions will be copied. Okay, and then from the backbone, after generating the backbone, it will generate the loops between the backbone and the secondary structures. Everyone is familiar with the secondary structures, right? Alpha helices and beta sheets, coils and loops, right? In this, after building the main coordinate locations from the template, it will be concentrating on the loop regions that are having more similarity with the template. The regions with the template regions, and that template regions coordinate will be imitated with the loop regions after backbone generation. And with this, it will complete the loop and backbone like completely. It will finish the backbone, right? Alpha carbon, carbon, beta carbon, and nitrogens. Everything will be. I mean, atoms coordinates will be copied from the XYZ coordinates. Okay, this is x-axis, and this is y-axis, and this is z-axis. So from all the three axes, it will be atoms will be positions will be copied, and the coordinates will be imitated with the template that is identical. Okay, and then side chains. Similarly, the side chains information from the template coordinates will be generated from for the target, and then model will be refined. For this model refinement of the for the built model, it will be done in energy minimization process. For energy minimization, we need force field. Okay, force field, we have force field is another biggest one of the important topic. So using force field, energy minimization is done, and we have many types of force fields like charm, amber, and chromos, and OPLS 2005, OPLS 2007 versions are there. So these are amber, charm, chromos are free. I mean, sorry, chromos is free. Charm and amber are commercial thing. OPL is also commercial force field. Okay, all these force fields are used to minimize the built model, such that energy minimization is important, and it is done just to bring the generated model from higher energy state to lower energy state, as I explained the very first. Because low energy state is nothing but yes, sir, yes, yes. Any doubts? Is it fine? Okay. Low energy state structures are said to be the native structure, because at low energy state it can exhibit its function fully. So we are energy minimizing the build structure from generated energy to lowest energy state. So it will become as a, it will fold into a native structure. Okay, and you can see the dynamics in minimization, like simply it is bringing to the lowest energy state. Okay, energy minimization can be done through molecular dynamic simulations. That is also another important and big topic in bioinformatics and biophysics. Okay, and after all this model building and refinement, we'll go for validation. So I'll just recap this model building. We'll perform blast. Blast is okay. Blast we are doing for template search. In template search, we'll go for alignment. Alignment, and then from alignment, we'll go for improvement of the alignment. Improvement, and then we'll go for building. Model building. After building the model, we'll be refining it. Okay, refinement. After all this, we'll get homology model structure. This homology model structure should be validated before used in docking studies or any other studies. Okay, this is a short recap of model generation. Is it fine from here up to here? Any doubts you can raise or discuss about this? I think students and participants can raise or discuss any doubts up to or clear up to this, up to model generation, homology modeling. Anyway, theoretically, anyway, my hands-on will be performing. Theoretically, is it okay with you people up to here? I think no questions.
Dear participant, if you have any question, please feel free to ask. So you
Because
can unmute and ask your question directly from the speaker, or you can put your question in the chat box also.
yeah, you can give the question chat box also. Fine.
Some of the participants are asking about the content which are being presented. These content will be provided to you after the session, after
Yes.
each session. Okay, don't worry about that. And also, if you are registered on the platform, Mathtech Edu, you can download from your account also. Okay.
Yeah.
We will
I
share in
think
the WhatsApp group as well as on your account. If one is joined the meeting late, don't worry. The recording of each session will be available. Okay, you can log in the account and watch each video. And also, we will provide you the link of each video to all the participants.
okay. So shall we resume again? Yes. Yes.
Yes, sir.
This is the what we have seen up to now, like searching the template from the blast and alignment and improvement of the alignment, and you're building based on the script. And then after running the script, you'll get the model. After that, you'll be refining, and then we'll be validating. And this is how we are supposed to validate. Okay. Like for example, this is a model structure we have generated and how it is validated. So, okay, I'll clear this. Okay. So this is the basic peptide bond, CONH bond. This is one amino acid and this circle is another amino acid. Okay, one amino acid is bonded with the adjacent amino acid based on the CONH bond, right? This CO yeah. In when two amino acids are joined, water molecule is H2O is released. H2O water molecule is released, and this Alpha carbon means beta carbon and oxygen, and nitrogen and hydrogen. These are bonded. This is like CONH bond. This is nothing but peptide bond, right? This CONH bond is peptide bond. When two amino acids are bonded each other, water molecule is released or generated. After leaving the water molecule, CONH2 is bond like peptide bond. This peptide bond will be defined as the pi and psi angle. This alpha carbon to carbon and alpha carbon to nitrogen and beta carbon to nitrogen. So these angles between these atoms, like pi and psi angles, we can see here alpha carbon to carbon and alpha carbon to nitrogen, carbon to nitrogen, right? And alpha carbon to carbon. So these torsion angles between the atoms, that two carbon alpha carbon and carbon, alpha carbon to nitrogen and carbon to alpha beta carbon to alpha carbon, will define the stability of the protein structure we have generated. Because alpha carbon to bond length and torsion angle between alpha carbon to beta carbon and alpha carbon to nitrogen, nothing but that pi and psi angles, nothing but pi, sorry, pi and psi angles. So these two torsion angles are predefined. So based on this, we'll be defining the structure, we'll be validating the structure, model of the structure we generate is good or not. Okay, so you can see this carbon to alpha carbon, nitrogen to alpha carbon to carbon, and carbon to nitrogen, beta carbon to nitrogen. So from this, it will be validated based on this. These are predefined. So based on this, it will be validated. For simple, okay, for simple validation, we can done like we can do RMSD. RMSD is everyone might be familiar, like root mean square deviation. Okay, we will overlap with or superpose with our template structure what we have considered for generating the target structure, homology model structure. Okay, so these two template homology model structure we have generated model will be aligned to template, and RMSD scores near to 0 will show the best model, and near to 1 will mean near to 1 or above 1 shows the higher the RMSD value, there is a more deviation with the template. Near to the 0, it is more similar to the template. Okay, so based on the RMSD also we can validate. And apart from this, based on the pi and psi angles, the torsion angles between the carbon, alpha carbon and carbon and carbon nitrogen, we can define the structure. This is Ramachandran plot. So GN Ramachandran from our India have done from biophysicist done on the amino acids structures, and he have defined some predefined bond angles for the 18 amino acids by that time. Later it was developed for all the amino acids. Okay, based on that, I have generated four quadrants. based on the psi and pi angles. Okay. So while these quadrants, we can see we can represent it in four different colors, like white, red, yellow, and pale yellow. So white shows the disallowed regions. That means the residues from the model we are following here. For example, in this tyrosine 85 from the example model is following in this white. That means this residue is following disallowed region. That means the bond length or bond angle between the pi and psi angles are not within the limit of the known angles. This is not following the natural one. That means this is far away. This is exceeding one. So this residue is not cannot be considered from this model. Okay, and the residues falling. See the black dots in the red region. This shows they are allowed. They are following the optimum bond angles between the residues. And see here, this yellow region, these are generously allowed because of steric classes or longer bond length. It might be falling in these regions, or else with normal bond, optimum bond length, it come under red regions. Okay, so these are red is like allowed, yellow is the generously allowed. These are mostly allowed. We cannot discard this pale yellow also, but residues falling in white or disallowed region, yellow residues. That means those residues shouldn't be considered. See, here you can see the phi and psi angles between the alpha carbon to nitrogen. Okay, see here alpha carbon to carbon and alpha carbon nitrogen angles. So residues falling in these will be the having more phi and more psi angles, and residues falling here will be the low, high psi and pi angles. You can see here pi and psi both will be 90-90. That means this is disallowed, disfavored. It will fall here, right? This means it will fall in this region. This is disallowed region. Okay. So this is that this yellow and red. This one is a older traditional Ramchandran plot. Present day Ramchandran plot was representing like this: blue, dark blue, light blue, and white. So this is the present day Ramchandran plot has been showing the report like this. Previously, it was the older one. Okay. Yeah. This is the thumb rule. I mean, like as we discussed here, these pi and psi angles, we can define based on the region. We can define which region it was present. I mean, what is the secondary structure of this residue? Residues falling under this region, like this first quadrant. Mostly, it will like beta sheets. And regions following here will be the helix. How we can say that? By seeing the report, we can say these residues falling here in this quadrant will be helices. So how we can say that? Like, see, alpha helices we have the terminus from one end to another end, like this flow. See here, 1, 2, 3, 4. Here, okay. Here you can see in this image, right-handed helix, left-handed helix. You can see the residue, starting residue one, first amino acid, second amino acid, third, fourth, fifth, sixth, seventh, eighth amino acids. The angle between this alpha carbon, second residue to third residue, you can see what will be the angle here. It will be near to 45 or less than the 90 degrees. So this will be near to 45. So minus 45. When compared to the left hand helix, right hand helix, it will change. Okay, based on this, we can say, based on the angles, we can say the rotation of the secondary structure of the proteins. See, in case of beta conformation, it will fall in the first top quadrant, top left quadrant, because the angle between the sheets you can see first from one amino acid to another amino acid, beta carbon to alpha carbon, pi and psi angles will be like near to 180, right? One amino acid to another amino acid, the angle will be near to 180, more or less. That means this will fall under the top quadrant in this quadrant. Okay. So by seeing the Ramsden plot report also, we can define the secondary structure of the proteins. So this is in beta sheets. We can have the both parallel and anti-parallel sheets. Okay, and beta turns also you can see here. The type 1, type 2 beta turns. Okay, all these beta sheets also will having the pi and psi angles near to 180 degrees.
You why don't you eat this? Mm-hmm.
Some noise is there. Any doubt or noise?
You that have eaten rice on the morning. You don't know the mother is supposed to eat.
I think some interruptions. Fine. Okay, you can see the based on the quadrant regions they are following. We can see what will be the residues falling in these quadrants. See, in this quadrant, we can find the angles between minus 0 to minus 180 and minus 180 to 0. That means that residues will be having right-handed alpha helix, right? And if the angle between pi and psi angles is from plus 0 to plus 180, or in that case 180 to 0, in that case it will be like left-handed alpha helix that will be falling in this quadrant, right? If the residues are between near to plus 180 in this quadrant, here that will come as parallel beta sheets, and based on that beta sheets, the angle from 0 to 180, 0 to 90, 0 to 180, based on these positions, we can say it's a beta sheets, right-handed beta sheet, I mean parallel beta sheets or anti-parallel beta sheets. Okay, based on the angle positions, you can see the quadrant. You can check parallel beta sheets and anti-parallel beta sheets, right? So this is the how we can validate based on the if more than 95%.
Abby. What is Abby?
More than 95% of
Lecture topic.
residues present in the allowed regions, we can consider that model as a good model. I think participants can mute. Okay. Structures having more than 95% residues in allowed regions, and generously allowed region means red and yellow, that is considered a good model. But we can have to refine the remaining 5% of the residues. By model refinement method, we can build the 100% good model. Okay, in case of Ramchandran plot, we can't get the glycine residues values and prolines values because they are somewhat fixed and they're very small to show the steric hindrances between the amino acids. So less steric hindrance because of the very small size, so we can't get these glycine residues in the Ramchandran plot. Same cause of proline also. Yes, they'll show the steric clashes, but the chain bond length is somewhat fixed. So this F value of the proline will be like fixed. So and the steric classes will be exhibited, but they are unique. So this glycine and proline will not be displayed in the Ramchandran plot. Okay. So apart from these two residues, remaining residues will be displayed in the Ramchandran plot. Okay, and then I think some. Okay, this is what homology modeling, and we'll go for threading or fold recognition method. In this, okay, as I said, threading and homology modeling both are knowledge-based method. It needs template. In case of threading, it needs the knowledge of the sequence, like how they are aligned or how they are local folds. It will not consider the entire sequence. It will consider the local folds that are promising. Okay, that means similar to the backbone structure. It will define the. It will compare the backbone's fold to the template, not the entire structure to the template. So this will separate the solvation potential of the three-dimensional structure to define the model. Okay, so one backbone's fold structure will be compared to the sequence of the target. That this is the basic difference between the comparative model, homology model, or fold threading method. Okay, that means here sequence alignment is done against the sequence only, not the known structure, entire structure. But in case of homology model, we are comparing against known structure, that is complete structure. Here only known folds. Okay, based on the alignment score from the structure and sequence alignment and identical fitness or potential score and some deletions. Based on all this, it will generate the model. Okay, and a de novo method or ab initio method or fragment based method modeling is another method. Here, to use energy scoring functions will be used more for the model building itself. Here, uh, sorry, here more native like structures will be considered with the all the parts, like it will break the sequences into number of secondary structures, or it will break the structure into sequence into a minimum number of residue fragments. For example, if you are giving hundred residues of amino acids for threading process, I mean like ab initio method, these 100 residues of amino acids will broken into 10 residues length or 6 residues length of polypeptides. Like all the 6 residues, 10 residues, like this, it will make 10 polypeptides. Or in case of length is 6, it is broken into 6 residues. It will make 6 in 600 by 6. Okay, that many number of fragments is done. For each fragment, again it is built. Okay, individually it is built. After building the each fragments, those fragments will be linked together based on the Monte Carlo optimization method, and finally to generate the uh, model. And this model will be give like empirical like summation of the all fragment models to generate the complete protein model. Okay, like small fragments is modeled into one structure, local structure, and all the local structures are joined combined to form a global structure. Okay, and this using energy minimization is compulsory for this. And one of the server most popularly known server is Rosetta server. And this is how we can visualize the structure using PyMol. PyMol I just shown here in some secondary structure. You can see the alpha helices in cyan color and beta sheets in purple, and co-crystal ligand in black.
This Indian.
And remaining things are coils and loops. This is just visualizing PyMol visual. It's a GUI in a graphical user interface. And here just another example for visualizing interactions after docking. We can see the ligand and receptor interactions for the individual residues, and this blue dot showing the hydrogen bonds involved. Okay, and thank you for the patient listening. Hands-on and hands-on will be doing the thing properly and slowly. I think any doubts you can raise your raise the doubts now, or you have open for discussion right now. Can have a discussion of doubts also.
What's in the doctor? Why you don't know what you're doing? Trying to stop them. Critics me.
So shall I stop the sharing?
I don't know what the problem is. No.
Dear participants, if you have any question, please.
We've asked our question, answer the one we have asked now.
Yes, you can open for discussion. You can ask for question, any doubts or some short recap.
Okay, my question is, can you hear me?
Yes, yes,
Okay, yeah, is the about the validation.
yes, sir. What the doubts, sir?
I didn't get the last slide on the validation that you presented. I don't know if you can go back to the last slide.
Last slide of validation.
Yes.
Okay. I think I have to share the screen. Okay. So this one or this one? So am I audible?
Okay, yeah, the first one.
This one, sir?
No. The one you showed before.
Previous
this.
one.
Yeah, the chart, the plot. Yes, exactly.
Yes, sir.
Okay, I'm trying to see how you mapped this one, whether it's going to be a right-handed alpha helix or whether it's left-handed with the plot
Okay.
that's on this side. Yes.
Okay. Your doubt is how I plotted this as a left-hand
Yeah.
helix and
Yes,
how
how you go
this
about it.
as right-hand helix, right, sir?
Yeah,
Yeah.
exactly.
Okay. I'll clarify this. Actually, I have mentioned this in previous slide itself. I'll just recap it. This is the region how I can define. So this is a region. See here. So from amino terminus to carboxy terminus. Like first, whenever we can see uh, N terminal to C terminal amino acid, we will be checking now, sir. From one amino acid to another amino acid, peptide bond is formed. Then we'll say as N terminal to C terminal, right? In that case, first amino acid to second amino acid. Here, the alpha carbon to beta carbon, pi and psi angles between 1, 2, and 3 will be falling. Here, see, this will be the positive. Just simply you can check this, sir. You can see if my hands are visible. From first residue to second residue. This is, for example, these two are two thumbs or my one of the amino acids. From first amino acid to second amino acid, if are near to 180 degrees, these are both peptide bond is near to 180 degrees, it will be falling in top or left top quadrant. In case of if it is like this, from you can just fold the answer. If you just hold like this thumbs up, you can see the first thumbnail as the first amino acid, and the second index fingers nail as the second amino acid. You can see the angle. This nail, consider this nail as amino acid, okay, and consider this nail as a first amino acid, and this as a third amino acid. If you see this, if you are folding the helix, the angle between the first amino acid and the second amino acid is rotating here, means reducing. The angle will be near to 0 or near to 45 if it is right hand helix. If it is left hand helix, it will be positive. It will be like this. First amino acid and second amino acid, right? Helix will be like this. You got it, sir? You can see this number here in this slide, like this. Sorry, not this. Here, this angle. One second. You consider this numbering this image, sir. Angle between these shows the alpha helix and right hand helix. If it is left hand helix, this entire thing will be upside, reverse. Okay. Based on this, I can say with this plot, I can say the angle from 0 to minus 60 will be right-handed alpha helix. See, first, let us say this is my first thumbnail as a first amino acid, and second index finger nail as a second amino acid. See, the angle is going lesser from 0 to lower, the minus. So it will be like near to 60. If it is 90, it will come here. One will be both will be here, top and down. So it's not 90 and it is not equal. If it is equal, it will show like 180 degrees. So it is very less. That means it is turning down. That means less than 0 and not near to 90 minus 90. If it is plus 90, it will be like here, first and second amino acid. If minus 90, it will be like 1 and 2. It's not minus 90. That means near somewhere negative value near to 90. So the residues falling in these angles will be right hand helix. It will tend to fold to form a helix. So thus right hand helix will form in these angles, and the same consider this top. This will be falling as a left hand helix. Okay, you got it, sir?
Yeah. Thank you very much.
Yes, sir. Any other doubts?
Any more question, please? Some participants are asking about the content. The presented content will be shared in the WhatsApp group. Okay. Recording will be also there. When the recording will be available, we will share the recording in the WhatsApp group also. And all the sessions will be start at the same time. Actually, the actual time was 6 p.m. to 8 p.m. But we extend the time. In the place of 6 p.m., we are going to start at 6:15 p.m. according to Indian Standard Time. And the link to joining the session will be shared in the WhatsApp group at least 30 minutes before starting the session. So I think all of you will be available to join the session. If you have more questions, please feel free to ask.
I think in case
I think
Yes.
there is no more question.
yes, sir.
Yes. So it is time to end the meeting, and tomorrow we will start the session at the same time as we start today at 6:15. Thank you very much. Have a
Thank
nice
you.
day.
Thank you, sir.
Now we are going to end the session. Thank you, sir, for your nice presentation and really very informative for all the participants. And
Thank you, sir.
for me also, I enjoyed your lecture.
Okay.
Thank
Thank
you.
you, sir. Thank you very much.
Okay.
Now
Thank
we
you.
are going to end the session.
Okay. Thank you.